Equations can be used to model the real world. This expression models how much money I have each week, starting on May 1st. You write the number of weeks it has been since May 1st, multiply it by $300, which is the amount of money I make each week, and add it to $200, which is the amount of money I started with. I'm saving up for a gaming PC, so I want to figure out when I'll have $2,000. I'll make an equation which puts the expression with the amount of money I make on one side, and the amount of money I want on the other. Then I can use basic algebra rules to find out the value of t that makes both sides of the equations equal to each other. But not everything can be modeled with equations that are so easy to solve. This expression models the height of a spring that's damped, so it doesn't go back and forth forever, but instead just slows to a stop over time. I want to figure out all the times when its height is equal to 0.1, but what if I don't know about any algebraic rules I can use to solve it? What if there aren't any? Let's say I'm trying to find security footage of the person who stole my delivery of carrots from my front porch. I just know that one day they were there and the next day they were gone. The straightforward way to find the thief is just to watch the entire video, from start to finish, until I find the moment where it's stolen. But it turns out there's a much faster way. If I skip to the middle of the video, and the carrots are still there, then it must have been stolen in the second half of the video. Now technically, someone could have taken the carrots and subsequently returned them before the halfway point of the video, multiple times even. We don't know for certain what happened in the first half, but we do know that the box was definitely stolen in the second half. We can keep cutting in half the amount of video we have to watch, skip to the 75% point, and if the carrots aren't there, then they must have been stolen somewhere between the 50% point and the 75% point. If we want to find the exact minute it was stolen, then the number of security camera pictures we have to check is log base 2 of the total length of the video, which is much better than having to watch the entire length of it. So, this is a very effective root finding method. Finding where an expression equals 0 works the same way. You keep shrinking an interval which is positive on one side and negative on the other, until you find the exact point where it crosses over the x-axis. This is how you solve equations with an expression on one side and a 0 on the other. But what about equations which have expressions on both sides? Just rewrite it by moving them both to one side. This method of shrinking a bracket until you find a 0 is called bisection, and it's the most basic and reliable tool in your toolkit. You don't have to cut the bracket exactly in half. You could also draw a diagonal line from one side of the bracket to another, and investigate where it crosses the x-axis. This is called the false position method. There are many different algorithms out there. Some of them are fast but can miss a root, but others take their time and make sure that they always find one if it is there. And the bisection method and the false position method, those are the slow and steady ones. Another strategy is to start with an initial guess of where the root should be, and find out which way you should go, left or right, to get closer to 0. Looking at the slope of the curve tells you exactly how to do that. Assuming f of x is above the x-axis, you want to go down, and if the slope is positive like this, then you go down by going left. A steeper slope means you can get to 0 in a shorter distance. You can think about the tangent line of a curve as sort of a simplified version of the function around that point. It's accurate exactly at that point and around that point where the line is tangent to the curve. Finding the root of this simplified function is super easy, so it's used as a way to estimate how to get closer to the root of the actual function. Newton's method finds the roots by calculating the tangent line of an initial guess, finding where that line crosses the x-axis, and using that position as its next guess. Newton's method needs to calculate the derivative f prime of x at all of these positions, but if you don't want to do that, then you can just use the average rate of change between that point and another point close to it. That's called the secant method. When you use a parabola instead of a line to estimate the function, that's called Muller's method. You don't need brackets for a Newton's method, but you do need an initial guess of where the root might be. If you use a bad guess, the results could be disastrous. Try to use Newton's method to find the 0 of this function, starting with this initial guess. First, draw the tangent line at that point. Where do you think the next guess should be? Right, it's where the line crosses the x-axis. Find where the function is at that x value, and draw a tangent line at that point. Again, let's see if you can find out where the next guess will be. That's correct, right there. Notice how it's further away from where we started, which is the opposite of what we want. As Newton's method continues, it runs away from the actual values that we're looking for. Also, take a look at this function. If it ever stumbles upon one of these points, it'll get stuck in an infinite loop going back and forth from one point to another. In summary, this method is faster than bisection, but it won't always work. To strike a balance between speed and accuracy, Brent's method chooses between multiple different strategies, trying to do the fast ones before falling down to the slow and steady ones if necessary. Brent's method uses the bisection method, the secant method, and a third method called inverse quadratic interpolation. Root-finding methods are judged based on how quickly they track down the correct answer. Each step of the process gets you closer and closer to the answer, but some algorithms converge on a root faster than others. In other words, you want your guess to be closer to the actual value than your previous guess. Just how fast an algorithm gets closer is measured by something called the order of convergence. Root-finding algorithms are an active area of research and are used everywhere in the real world. If you want to calculate the value of a stock price or find the position of a particle in a turbulent fluid, you need to use equations which are too complicated to have easy solutions that you can find with algebra. With root-finding methods, you now have the power to solve any equation.